One of the most common error detection techniques used in data communication and storage is the CRC, the cyclic redundancy check. And it's similar to a checksum. And in fact, in some cases, you'll hear it called a checksum, but it's not a sum like this. You're not adding up all of the different characters and coming up with some sort of check sequence here. Instead, what you're doing is instead of representing it as a bunch of individual numbers and adding them up, you're representing your entire message essentially as one big, long binary number. And then what we can do is we can do math on that one big number to try to come up with some sort of check sequence. So just as an example, and this isn't exactly how CRC works, we'll get to that in a minute here, but just to kind of get you a sense of where we're headed with this, I've got two messages here, and the only difference is just these two letters have changed. So the O changed to an N and the R changed to an S. So essentially we subtracted one from the O, we added one to the S. And this is an interesting change because this is something that the checksum wouldn't catch, because if we're subtracting one number and then adding another, that doesn't change our overall sum. So we wouldn't catch that with a checksum. But if we represent our entire message as one big long binary number, it does change that number. And just to give you a sense, like this binary number can also be represented as a decimal equivalent. And so this is actually what that is for these two messages. And so you can see this is just this big long number. This is the decimal equivalent of this big long binary string. And you can see because we've got two changes here, the number is very different. And in fact, if we do some basic math to it, you'll see some other differences. So for example, if we divide both of these by 251, well, then we get some big long answer here. But then there's a remainder as well of 50. If we divide this other number, which represents this other message, by the same thing, 251, then we get a different answer, but we also get a different remainder. And so you can imagine what we might do is send our message along with this remainder. And then on the other end, when we receive the message, if we receive the message and it has some corruption like this, when we do that same division and compute the remainder, we can see that the remainder is different, and we can use that to detect that there was an error in receiving our message. So this simple division like this is actually a bit simpler than the way CRC really works, but I think it's going to be a useful analogy to walk through an example of before we actually get into how CRC really works. So let's take a simpler example here. Instead of hello world, we'll just use the message hi, exclamation. So it's just 3 bytes. So that way our numbers that we're dealing with are a little bit smaller. And so what we want to do is we want to transmit our message hi, and then we also want to transmit some sort of check sequence. So what I'm going to do is actually add a few extra bytes, actually 2 extra bytes here, so 16 bits of all zeros. And what we're going to do is we're going to fill these extra bytes in here with our check sequence. So our overall thing that we're sending is going to be this big long number, but we're going to change some of these zeros to actually get the full message. But if we leave these as zeros for now, we can convert this entire long thing into a decimal number, and we end up with this number here. So again, we're treating our entire message as just a number. And so what we can do is we can then divide this number, divide our message by some other number. And so I'm gonna divide it by 65521. And it's actually sort of important what number you choose to divide by. And it might be interesting to think about why that is, but we'll get back to that in a minute here. But if we divide this message, as represented by this number, by 65521 and look at the remainder, when we do that division, the remainder we get is 26769. And so it's this remainder that we're going to use to sort of form the check sequence that we're going to add onto our message. But we don't want to just stick that 26769 in there. What we want to do is actually something a little bit more clever, which is take the number we divided by, 65521, and subtract that, and we end up with this difference here. And if what we do is we use that difference then and add that to our original message, we get this new number. And you might be wondering, well, why are we doing all this? Well, the reason we would do this is because this new number that we get is now going to be a multiple of 65521. And it's going to be a multiple of 65521 because we took this other number and we figured out what the remainder was, and we tacked on the extra bit to get from that remainder to the next multiple of 65521. And so basically this number is just the next multiple of 65521 after our message. And in order to get there, we needed to add on this extra 38,752. But what that means is we can take this 38752 and encode that in these last 2 bytes here. So remember, we had all zeros here. If we encode that 38752 in there, then that gives us our entire message now equals this thing, which is now a multiple of 65521. And so now what we get is we get this entire message that we can send that has the message we want, hi, as well as some extra bit here. But the entire thing, if we think of it as just a single number, when we divide that number by 65521, the remainder will be 0. And that's what we can do to check or to verify that we received the message correctly. Because if any of these bits changes, then it's very likely that it will no longer, the overall thing will no longer be divisible by 65521. And that's whether one of the bits in our message changes or one of the bits in our little check sequence over here changes. If any of those bits changes, then there's a pretty good chance that it'll no longer be divisible by 65521. And so if we receive a message that's not divisible by 65521, then we can come to the conclusion that something might have been corrupted. So for example, if our message changes from hi to ho, because these two bits here changed and corrupted our message into something different than what we wanted to send, then we'd be able to detect that, because if we then take this new big long binary number and we take the value that it represents and divide it by 65521 again, the remainder is not 0, it's something else. It's just 23040. And because that remainder is not 0, because this message is not divisible by the magic 65521 number, then we can conclude that the message got corrupted and that the message ho is not the message that we intended to send. Now you might be wondering, why did we choose 65521 to divide by? Like, why that specific number? And does it even matter? Can you just divide by anything? Well, it definitely matters. It matters a lot, actually. And the thing that you choose to divide by here has some bearing on the types of errors you're able to detect, or at least the specific error patterns that you're able to detect. So to sort of understand why that's the case, let's look at this same example here, but break it down a little bit. You can imagine we have our transmitted message here, which is hi, along with the correct sort of division-y checksum thing that we're using here, and we get this number. And then we have the received message down here at the bottom, which has these two bits flipped, and that's this other number. But one way to think of this relationship here is that the received message is equal to the transmitted message plus whatever error occurred. So in this case, these two bits got flipped. So what happens is these two bits flipped equals this other number. And so you can think of the received message as being the transmitted message plus that error. And this is kind of a helpful way to think of it, because we know that our transmitted message is divisible by whatever number we're dividing by. So if we're dividing by 65521 in this case, we know that our transmitted message is divisible by that. And so for the received message to be divisible by that, in order to receive it correctly, the transmitted message plus the error have to be divisible. Well, we know the transmitted message is already divisible by that, so we can almost just sort of ignore that. And so what this is telling us is that as long as our error is not divisible by, in this case, 65521, then we'll detect that there was an error. So in this case, our error is this number here, or this binary number here, if you want to think of it that way. That's not divisible by 65521, so we're able to detect that error. But if instead of 65521 we had some other number, let's imagine we were dividing by 256. Well, if we're dividing by 256, this would be a multiple of 256. Anything where the last 8 bits are zeros is a multiple of 256. So there's lots of multiples of 256. So almost any error that we would have in our entire message would not be detected if we were dividing by 256. So that would be a terrible choice of something to divide by. Whereas 65521 is maybe a much better choice. It happens to be a prime number, and it's actually the largest prime number that fits in 16 bits. So that makes it a better choice. But ideally, what we'd want to be able to do is think, mathematically and very rigorously about what are the multiples of the number we're dividing by, and what do those bit patterns look like. And that's actually very hard to do, because you can imagine if we were intending to send the message ho, H-O, and this is what our message looked like. Our checksum here is a little bit different, right? Because it's a different message. And so the overall message number is going to be different. But if what happened was our message ho got corrupted the other way into hi, so those ones turned to zeros, then the error that we, I guess, essentially would add kind of in this equation here to get to our new message would be a very different sort of bit pattern than the bit pattern that we had here, even though it's the same two bits that are flipping. And so this ends up being actually pretty hard to reason about. So if we're trying to think of what is the best thing to divide by here in order to catch the sorts of errors that we might expect. So maybe we expect something like this. We know that our transmission medium works a certain way. There's certain types of errors that are likely to occur. And one of those types of errors that's likely to occur is 2 bits in a row get flipped. Well, here we have an example of that. 2 bits in a row get flipped. And our error here is just 2 bits. And so then we can think about, okay, what are all of the possible sort of 2-bit values that are in here? And then we can think about what number might we choose where none of those 2-bit patterns is a multiple of that number. And if we can actually find a number that matches that, then you'd think, well, maybe we can actually guarantee that any 2-bit error we're able to catch like that, or any 2 bits in a row, or whatever type of error we might expect. But here we have 2 bits in a row that get flipped, but our error has a whole bunch of bits that are flipped. And so the problem we're having here is actually related to place value, right? Because if we add 1 plus 1, we get 0, and then carry a 1 over here, and then add 1 plus 1, we get 0 again, and carry a 1 over here. And we just end up with this sort of rippling effect that leads to this whole mess here, that even though only 2 bits actually got flipped between our transmitted message and our received message, it's not necessarily easy to just look at that error component and see a relationship between the error and the actual bits that got flipped, like you might think there is if you just look at this one example here. And so all of that actually makes it much more complex, in fact, very complex, to think about what number we would divide by to look for certain bit patterns in our error. And so because of this, CRC does something different and actually quite clever. So CRC doesn't represent the message as a number like this. Instead, it still represents it as a mathematical expression, but it represents it as a polynomial. So check this out. Let me show you an example of how that works. So here's the letter H, and here's how we'd represent that in binary. So if we're actually transmitting the letter H over a network, these are the actual bits that we would send. And as we've been seeing, we can think of that as a number, in this case 72. And the reason that we think of that as 72 is that each of these bits has a place value, right? So if we just sort of expand this out, this is the same number. And what we're doing when we convert that to 72 is we're just saying each of these bits has a place value. So this bit all the way here on the right has a place value of 1. 2 to the 0 is 1, right? This bit here has a place value of 2, 4, 8, 16, 32, 64, and 128, right? Those are just powers of 2. And what we do is we just multiply each of those powers of 2 by the bit value, whether it's a 0 or 1. So in the case of 0, we essentially just ignore that term. In the case of 1, then we have a 2 to the 6 plus 2 to the 3rd. And 2 to the 6 is 64, 2 to the 3rd is 8, and if we add those together, we get 72. So this is just how we get 72. This is how binary numbers work. One property of this is if we add another 8 to this here, we wouldn't have 2 times 2 to the 3rd because 2 8s here makes a 16, right? So you'd carry that 16 over into the next place. And so you'd have 1 2 to the 4th instead of 2 2 to the 3rds, right? And because you have that carrying between places here, that's basically how you can get lots of bits changing here in the mathematical difference if you subtract, even though only 2 bits actually changed. You have that carrying effect. So a trick that CRC uses to avoid carrying is to basically do the same thing, but replace all the powers of 2 with powers of x. Now each term is truly independent. If we add another 1 to this term here, it doesn't carry over. We just get 2x to the 3rd. It doesn't touch the x to the 4th term. And just like before, we can simplify by getting rid of all the 0 terms and end up with just x to the 6th plus x to the 3rd. And so this is just a different way of representing this same binary string. Now, it certainly looks a little bit weirder than just a number, but it's another expression. It's a way to represent the same binary message here, the same binary string. And you might be wondering, what the x is or what it represents. And it's sort of weird. It doesn't really represent anything. I guess you could plug 2 in here and you get 72. You get the same thing. But the idea is it doesn't have to be 2, or really doesn't have to be anything. So x doesn't really represent anything. It's just part of this trick that we're doing that just gives us a different way to represent our message. But the important part is that even though x doesn't really represent anything real, this expression we end up with is still an algebraic expression, just like 72 is. So we can still do math to it. And in fact, we can still divide it by stuff and get remainders and everything else we were doing before. It just looks a little bit weirder. And so we can do the same thing with a bigger message, like our message hi. So we have our message hi, and then we have 16 zeros over here, and this is where our checks are. Actually, eventually, this is where our CRC check is going to go. But we can convert this to a polynomial like this the same way. And this is what we get. And so what you see is if you sort of count over here from 0, 1, 2, 3, this is the 16th bit, and that's a 1. And then you go 17, 18, 19, 20, 21. So that's why we have the x to the 21 term. 22, 23, 24. We have our x to the 24 term, and so on. So each of these ones turns into a term in our polynomial in the appropriate position. And so maybe it was a little bit weird at the beginning of the video to think of this message, this entire message, as just one big long number. And maybe it's even weirder still to think of this message as a polynomial, but it's a perfectly reasonable way to represent the message. And because it's a perfectly good algebraic expression, we can do math to it. So we can even divide it by something. So for example, it looks a little messier here, but here's our polynomial right here under our division. It's the same thing. That's our message. And we can divide it by some other number, or some other polynomial actually in this case. And again, it does matter what you divide by, and we'll get to how you might choose that and what that actually means, but it is going to impact what types of errors you can detect. But for now, we'll just use this one that I've got here. And if we divide our message by that polynomial, you get some answer, and it's some big, long, messy polynomial. And then you can multiply these two together, and you get some other thing. And if you subtract that, you get a remainder. And so this remainder down here is in fact the remainder when you divide our message by this polynomial. And that's the exact same thing we were doing at the beginning of the video, right? We have our message here represented as a number. We divide our message by some magic number, and we get a remainder. Here, same thing. We've got our message represented as a polynomial. We divide it by some magical polynomial, and we get a remainder. And then we can use this remainder then to kind of fill in the remainder, as it were, of our message here, so that our entire message then is divisible by our magical polynomial. But unfortunately, we've got a bit of a problem here. I don't know if you've noticed here, but if we want to take this polynomial and use that to determine the little remainder bit here to fill in the check sequence in our message, we've got to figure out how to convert this polynomial back to a binary representation. And so you say, okay, well, you just look at each position here. So in the 15th bit position, that's here, we put a 6. Well, wait a minute. There's no such thing as 6. This is a binary number. So we've got a bit of a problem here. What do we do with this 6? We've got like negative numbers in here. Well, the 5th bit position is a -1. We've got a 2 over here. So it looks like we've got a problem here. But fortunately, there's another mathematical trick that we can use that will help us out. And so the mathematical trick we can use is this thing called finite fields. And so let's do a quick sidetrack into what finite fields are. And so to understand what that is, let's talk about algebra here for a minute. So algebra is basically this set of rules that you can use to manipulate symbols. So for example, if we want to solve this for x, we can apply some rules. We can add 5 to both sides. We can sort of simplify this, and we get x over 2 equals 12. Maybe we want to multiply both sides by 2, and that gives us x equals 24. And so even if we're just solving for x, anytime we're doing any algebra, we're just applying a series of rules. And so this rule here, where you're adding the same thing to both sides, it's called the additive property of equality. And there's this rule here where you can multiply both sides by the same thing. That's the multiplicative property of equality. And so there's all these different rules that algebra has. And by applying the rules, you can manipulate expressions in different ways to solve problems. And so algebra is just a bunch of rules that all work together and produce consistent results. But one thing that you'll notice that maybe you never even really thought about is that whenever you're doing algebra, you're using numbers. And the numbers that you use when you're doing algebra make up what's called a field. And so if you've ever done any kind of algebra like this before, you've probably done it with the field of real numbers. These are certainly all real numbers. And so as long as all the numbers that you're using are real numbers, then we can apply all the rules of algebra, and whatever manipulations we get when we use those rules are valid, and we can use those to solve problems. But algebra works for other fields too. So maybe you've used complex numbers. And complex numbers are just a different field, but all the rules of algebra, as you know, work just as well. But we're interested in a finite field. And as the name would imply, instead of having an infinite number of numbers, like the real numbers or the complex numbers, a finite field uses a finite number of numbers. But still, all the rules of algebra work just the same. So how does that work? So what is a field? So a field is basically just a set of numbers, and then a definition of how you add those numbers together and how you multiply those numbers. And that's basically it. But your field has to obey certain rules in order to be a valid field, in order for algebra to still work if you use that field. And so there's certain field axioms. So for example, there's this axiom of associativity. So however you define your addition and multiplication, it has to be associative. It also needs to be commutative. So a plus b has to equal b plus a, and same with multiplication. You have to have identities. So there has to be an additive identity. There has to be some number. So you've got this set of numbers that are in your field. You've got to have one of those numbers has to be an additive identity, so that if you have a plus that number, usually 0, you get a. Same thing for multiplying. Essentially, you need a 0 and a 1. You also need to have an additive inverse. So something where if you add a number to its inverse, you get 0. You need a multiplicative inverse, which is some number, 1 over a, for example. If you multiply a number by its inverse, you get 1. And finally, your rules of addition and multiplication have to be distributable. They have to follow this rule of a times b plus c equals a times b plus a times c. And so within these rules, you can come up with any set of numbers and any definition that you want to of multiplication and addition. And as long as it meets all these rules, as long as your definition of what numbers are and what multiplication means and what addition means, as long as those rules meet these axioms, then your field, your set of numbers and your rules will work with all of the rest of algebra, which is pretty cool. So in our case, what we want to do is we want to be able to do algebra like this, where instead of getting 6 and -1 and 3, all we get is just ones and zeros, so that we can then nicely convert that back into a binary string here. So what we really want is a field, an algebraic field that we can do algebra with that only has 0 and 1 in it. So can we do that? Well, it turns out, yes, we can. And this is how we would define that field. So our field only has 2 numbers in it, 0 and 1. And then we can define addition like this. And it's easy enough to define addition because there's only 2 numbers. And so we can just list out every possible addition problem. And there's some weird things in here. So 0 plus 0 equals 0, you'd expect that. 0 plus 1, 1 plus 0 equals 1, you expect that. But then 1 plus 1, we're defining that as equal to 0. Okay. It turns out by doing that, then we actually meet all of our axioms with respect to how we're defining addition. Same thing with multiplication. Works pretty much the way you'd expect. Anything times 0 is going to be equal to 0. 1 times 1 equals 1. And just by defining addition and multiplication like this, we're meeting all of the field axioms. And so this is a valid field, even though there are a couple sort of weird counterintuitive things that you might not expect. So for example, we need to have this additive inverse. So you have to say a plus negative a always equals 0. So normally you'd think of like, oh, okay, 5 plus -5 equals 0. That's sort of the way that would work with the real numbers. But in our world, the additive inverse of a number is the number itself. So the additive inverse of 0 is 0. So 0 plus 0 equals 0. That works. And the additive inverse of 1 is also 1. So 1 plus 1 equals 0. Because we've defined this that way, then we can kind of check off that axiom there. And so you may want to pause the video and convince yourself that our definition meets all of these axioms. But it does. This definition here does meet all those axioms. And there's just a couple weird things. But we've defined all the weird things in just the right way so that they meet the axioms. And so again, you may want to pause and sort of convince yourself that that's the case. But because this is a valid field, that means we can use these numbers, just 0 and 1, only those 2 numbers, with this definition of addition and this definition of subtraction, multiplication, division, and all of the rules of algebra will just work in a consistent way, even though there are some unintuitive definitions in here. So if we go back to this gnarly polynomial division that we've got going on here, if we use the finite field when we do this division, we won't end up with all these weird coefficients, these, the 6 and the negatives and the 2 and so forth. We'll end up with just 1s and 0s as our coefficients. So let's actually work through this division problem using our finite field to see exactly how this all plays out. Okay, so again, this is the message we're going to send, hi, exclamation, and we're going to leave 16 bits here at the end to fill in our CRC. And because we're leaving 16 bits, the thing we want to divide by, this is called generator polynomial. I'm going to use a 16th degree polynomial so that we're able to make use of at least all 16 of those bits. So the message itself, shifted over, is this polynomial here. And I'm going to divide it by this same generator polynomial here. And again, I'll talk about how you go about choosing a generator, a good generator polynomial in a little bit. And so I set this up as this long division problem. And in fact, we are going to do long division that's very similar to the long division you might remember from grade school. And so the way we start is we basically look for how many times x to the 16th goes into x to the 38. And that happens to be x to the 22nd times, right? Because x to the 16 times x to the 22nd is x to the 38. And in fact, we can do that multiplication now. Now that we've come up with a term here in our quotient, we can multiply x to the 22nd times our polynomial here. And so x to the 22nd times x to the 16th is x to the 38, plus x to the 22nd times x to the 12th is x to the 34th. And then x to the 22nd times x to the 5th is x to the 27th. And then x to the 22nd times 1 is just x to the 22nd. So I just multiplied x to the 22nd times our divisor here, this generator polynomial, to get this right here. And so now, just like normal long division, I'm going to subtract. So we have x to the 16th minus nothing. That's going to be x to the 16th. X to the 21st minus nothing is going to be x to the 21st. And here we have nothing minus x to the 22nd. And so you might think, well, that's going to be negative x to the 22nd because we're subtracting this, right? This is subtraction we're doing here. But that's not true, right? Because we're using our finite field. And in our finite field, remember that 0 minus 1 equals 1, because we don't have a negative 1. We only have a 0 and a 1. So this is actually going to be a positive x to the 22nd, or the coefficient's going to be 1, I guess, because our coefficients can only be 0 or 1. That's the whole point of using this finite field. And of course, you might wonder, well, if we only have 0 and 1, well, how come we can have 22 here? And this isn't 22, I guess, in terms of being a number that we're operating on. This is really just 22 x's multiplied together. And so we can do that because we could just write out 22 x's all multiplied together. But in terms of the coefficients that we have, the actual numbers in our expressions, we're only using 0 and 1, and we're using our special addition and multiplication rules. Okay, so moving along, x to the 24th minus nothing is going to be x to the 24th. X to the 27th minus x to the 27th. Again, that's the coefficient 1 minus 1. And so 1 minus 1 is 0. We're not doing anything weird there, right? 1 minus 1 is 0. So nothing special, nothing crazy there. That just cancels out. So x to the 29th minus nothing is x to the 29th. X to the 30th minus nothing, x to the 30th. And then this term here, we have 0 minus 1 times x to the 34th. Again, that's going to be plus x to the 34th. Because again, even though we're subtracting, we don't have a negative 1 in our finite field that we're using. Okay, moving along, x to the 35 minus nothing is going to be x to the 35th. And then x to the 38 minus x to the 38, that's 0. So that cancels out. So that's the first step of our long division here, right? We figured out that our polynomial here divides into our message x to the 22 times and has a remainder of this thing down here. But we're not done yet, right? Because x to the 16th, we can divide that into x to the 35th as well. And that goes x to the 19th times. So we can keep going now. And we're going to basically just repeat this process and go through this entire polynomial here. So now we're going to multiply x to the 19th times our polynomial, write that down here, subtract, and keep moving. And so again, we can say that our message divided by this generator polynomial equals x to the 22nd plus x to the 19th, and it has this remainder. But we're still not done yet, right? Because x to the 16th goes into x to the 34th as well. And that goes x to the 18th times. So we'll add an x to the 18th up here. And now we'll multiply x to the 18th by our generator polynomial and subtract that off. And now this is our new remainder. But we're still not done, right? X to the 16th goes into x to the 31st, x to the 15th times. So we'll put an x to the 15th up here, add that into our quotient, and multiply that. And we'll go ahead and subtract. All right, still not done. X to the 16th goes into x to the 29th now, x to the 13 times. And now multiply x to the 13th times our generator polynomial. And then subtract. And now this is our remainder. The reason I'm doing this by hand, and I would encourage you if you really want to understand this, try doing a problem like this by hand, is that by doing it by hand, we start to see some patterns emerging. So one pattern is that we continue to subtract essentially this same polynomial. So we're subtracting something that's very similar to this polynomial, but shifted. And then kind of each time through, it's shifting over. But if you look at sort of the spacing, I guess, here, you can kind of think of that as the terms. It's shifting each time we subtract. And then the other thing is that the way the subtraction works is it's almost kind of like an XOR going on, right? Which is that when we do subtraction here, if one term or the other is there, then we see the term in the result of our subtraction. But if both terms are there, then we don't see the result. Or, obviously if neither term is there, we don't see the result. And so that's actually very similar to an XOR operation. So if we look at our subtraction, you can almost see, this is essentially, not essentially, this is the truth table for an XOR gate. So it's kind of interesting that there are XOR operations happening in here, and it's kind of interesting that we see this kind of shifting. So I'll just mention that I'm noticing some of those patterns emerge as we're doing this division, because actually both of those observations are going to be very important when we want to try to do all of this in hardware, because obviously shifting and XOR, those are things we can do in hardware. So we'll get to that though. But anyway, we're not quite done yet. In fact, I think we're about halfway through. So I'll go ahead and finish up the rest of this division. And so now, finally, x to the 16 does not go into x to the 13. So this is our remainder. And so because we used the finite field when we did this whole division process, what you'll see is that all of our coefficients are either 0 or 1, right? We don't have any of those 6s or 2s or negative numbers, anything like that in here. It's all just zeros or ones. So we could actually convert this remainder now to a binary number. But also, because we're using a finite field, the algebra is consistent. So one way you could check that is you could actually multiply the generator polynomial here times the quotient that we got when we divided, so this sort of answer that we got up here. If we multiply those two together and then add the remainder, you should actually wind up with our message. Because again, the finite field, even though it's kind of weird and we had to redefine some of the addition and multiplication a little bit, algebra still works, and that's the whole reason to use it. So anyway, we get our remainder down here, and we can convert this remainder now to a binary number. So this is the sort of x to the 0 place here. It's just a 1. So that's going to be a 1. And we're just looking at coefficients. So now the x place, the coefficient is a 0. There's no x term. It's just an x squared. So that's a 0. The x squared term is there. X cubed term is there. Each of these terms is there. X to the 9th term, not there. These terms are not there. So those coefficients are 0. X to the 12th term is there. X to the 13th term is there. And then we can fill in the rest, 14th, 15th, 16th. And so now we have this 16-bit remainder. And in fact, this is precisely the remainder that we can now include in our message here as the CRC. In fact, this is a CRC. We've computed a CRC using this generator polynomial. So to see how to include that, if we start with our message here, which we left 16 bits over here of zeros to leave space for the CRC, we can represent that message as this polynomial, and we can call that m of x. So m is our message. And then when we divide that by this generator polynomial, that's what we just did, and we end up with this remainder here at the bottom. And so what we can do is we can actually subtract that remainder from the message to get the transmitted message. Now notice I said that we're subtracting the remainder from the message. That might seem a little bit strange because it looks like what we did is added it here, right? Because we've got our message, which is this part here, and this message is represented right here, doesn't change. And then this part over here is the remainder, right? This x to the 13th, x to the 12th, x to the 8th, and so on, down here to x squared plus 1. That's the remainder. And so it looks like what we're doing is we're just adding that remainder on to our message. But technically what we're doing is we're subtracting the remainder from the message. And now it looks the same because, again, we're using this finite field where it turns out that addition and subtraction look like identical operations, which is admittedly a little bit weird. But remember, as long as we're following these field axioms, all of our algebra is going to work. And so that's why I say what we're doing here is we're subtracting the remainder from our message to get this transmitted message. And the reason to do that, to say that we're taking our message divided by our generator, taking that remainder and subtracting it from the message, is that so that the overall transmitted message is then divisible by the generator, right? Because, just imagine we have, instead of this polynomial, if we have a number, 1, 2, 3, 4, if we divide that by 10, we're going to get 1, 2, 3 with a remainder of 4, right? So we have this remainder of 4. If we take 1, 2, 3, 4 and we subtract 4, we're going to get 1, 2, 3, 0, right? So by subtracting the remainder, we get something that is now divisible by 10. Well, same thing here. Our message here, that you can think of that like the 1, 2, 3, 4. If we subtract the remainder from the message, then what we end up with, this 1, 2, 3, 0 now is divisible by 10. Same thing. Our transmitted message is now divisible by our generator polynomial. And that's very handy because then we can send that transmitted message to our receiver. And of course, we can encode the transmitted message in binary. And the first 3 bytes are going to look the same, so we actually we have our message retained in there. But then these last 2 bytes that started out as all zeros, now we're filling in the CRC. And so now if we transmit this over to our receiver, and the receiver receives that, if the receiver divides that transmitted message by the same generator polynomial, then it's going to get a remainder of 0, and that's how it validates that it received the message correctly. But of course, the receiver might not receive the transmitted message, T, exactly correctly, right? There might be a transmission error. So we might have a couple bits that get flipped like this. So in this case, what's received is actually this polynomial that has a couple terms inserted. This x to the 26th and x to the 25th bits got turned on, and so those terms get inserted into the polynomial. So now when the receiver divides this polynomial that was received by the generator polynomial, performing this same check, the remainder is not going to be 0, and so it'll detect this error. So another way to think about this is we've got our transmitted message T, and then when it's transmitted, there's an error that is sort of added to it. So we can have this other function we'll call e of x, which is the error. So in this case, it's these 2 bits, the 26th bit and the 25th bit that got flipped on. And so really what the receiver is doing, is the receiver doesn't know the transmitted message. All it knows is the transmitted message plus whatever error was introduced. So the receiver is going to take the transmitted message plus error, divide that by this generator polynomial, and then check if that's equal to 0. And if it's not, then it's going to detect an error. So just to look at another example real quick, here's an example where, again, the message we're transmitting is still high, but what we received is the message ha. And in this case, instead of 2 0 bits flipping to 1s, we have a bit that's supposed to be a 1 that flips to a 0. And so the polynomial that we receive is actually missing a term, right? The x to the 27th term that we should have has gone missing because that bit flipped to a 0. So in that case, what is, if we think about it in these terms, like what does that error look like? Well, it turns out that error just looks like x to the 27th, which is very convenient because it represents a single bit flipping in the 27th position, which is what happened. And this math still works the same way. Our transmitted message plus our error, which is what the receiver receives, if we divide that by our generator polynomial, we can check to see if the remainder is 0. And in this case, again, it's going to turn out that it's not 0, and so we'll detect this error. And so even though the bit flipped from a 1 to a 0, we don't have a problem with any sort of place value here because we're using polynomials. And we can still represent this error polynomial as being added because we're using the finite fields. And so those mathematical tricks give us this nice ability to represent this error polynomial as just a collection of the bits that flipped, nothing more, nothing less. And it doesn't matter whether they were flipped from a 0 to 1 or a 1 to a 0. Okay, so at this point, you're probably wondering, where does this generator polynomial come from? I just kind of threw this out here as this thing that we're dividing by without a whole lot of explanation. But why divide by this particular polynomial? Where does this come from? Well, it depends what errors we're trying to detect. So the receiver is doing this check here, right? It's taking whatever it receives, the transmitted message plus whatever errors. Of course, it doesn't know the difference. It's just receiving something. It's taking what it receives, and it's dividing it by that generator polynomial. If we get a remainder other than 0, then we know that there's an error, and that's how we detect errors. Now, we also know that the transmitted message without errors divided by the generator polynomial does divide in evenly. So really, the question, as far as whether this generator polynomial is going to detect errors or not, is whether the errors are evenly divisible by the generator polynomial. So if we know what these errors might be, that is, we know what errors we want to try to avoid, then we can try to be clever and come up with a generator polynomial that doesn't divide into any of those likely errors that we suspect we're going to get. So let me show you an example of how we can sort of reason about what our generator polynomial might need to be in order to detect certain types of errors. So for the simplest case, let's say we're just trying to detect single-bit errors. What type of generator polynomial might be able to do that? Well, let's think about what that error looks like. So we can kind of generalize here. So the error in this case that we're trying to detect is x to the I, where I could be any value. So for example, in this case, where our message was corrupted, we had a single-bit error like this. Our error was x to the 27th, right? Because it was the 27th bit position from the right that had the error. Well, if we want to detect any 1-bit error, then it's x to the I, where I could be anything. So in order to detect this, we need to come up with a polynomial that is not a multiple of x to the I, that wouldn't divide into x to the I. Well, that's easy. Any generator polynomial with at least 2 terms won't divide into x to the I. So, x plus 1 is kind of the simplest example. X plus 1, doesn't matter what I is, x plus 1 is not going to divide into it. So if we use this as our generator polynomial, we're guaranteed to detect any single-bit errors. Now, how about detecting 2-bit errors? This is a little bit more complicated, but we're essentially thinking about it the same way. We're going to think about what is the error that we're trying to detect. In this case, it's 2 bits, x to the I plus x to the j, where I and j could be anything. And this is, an example here. We see where we had 2 bits that changed. Our error was x to the 26th plus x to the 25th. So that fits this pattern here, but it could be any 2 bits. That's the idea. And so the goal is come up with a generator polynomial that is not a multiple of this expression. And it's a little bit harder, but we can rewrite the error like this. We're just sort of factoring out x to the j here. And so now we have 2 factors. X to the j is the same as before, right? That's x to the I. So we're not going to find a multiple of that as long as our generator has at least 2 terms. And so that just leaves us with this term over here, which we can just rewrite as x to the k plus 1, where you can think of k as sort of the distance between the 2 bits that have errors. And it's a little bit hard to come up with polynomials that won't divide into this, but there are some simple polynomials that won't divide into this unless k gets really big. So for example, this polynomial that we've been using here works as long as k is less than 32,751, turns out. And so in practice, what that means is that this polynomial will detect any 2-bit errors as long as the 2 bits are within this distance from each other, which if your overall message is smaller than this, then that's guaranteed to be. So if you have a message that's less than 32K, then this particular polynomial will be able to detect any 2-bit errors within that message. And that's the power of this method. We can rigorously mathematically prove that certain patterns of errors will always be detected. It just might involve little caveats about the message size, and it obviously requires a bunch of math. But with that in mind, we're guaranteed to detect certain patterns of errors. And if we know what errors are likely in our transmission, we can try to find a polynomial that's going to be best at detecting those errors. Now, in practice, you probably won't come up with your own polynomial. There are lots of different ones that have become international standards, and you can see a bunch of them here on Wikipedia. And I've been using this one called CRC 16 CCITT. This x to the 16th plus x to the 12th plus x to the 5th plus 1. And you can see it's pretty popular. It's used in a whole bunch of different things, Bluetooth and many other things you may have heard of. Another really maybe even more popular one is CRC 32, which is, as the name would suggest, a 32-bit polynomial. And you might imagine why I haven't been using this as an example. That last division problem would have been real fun with this one. But this is used in all kinds of things, including Ethernet 802.3 standards. So this would include all of your Wi-Fi, all kinds of things, as well as, again, many other things, PNG, things you've probably heard of. These are relatively old standards, but they're pretty good and they're used in everything. And so I would recommend just using them. But they aren't technically the best you can get. Finding good polynomials is actually quite a bit of effort. So it took many years for people to find better ones. For example, you can see here there's a couple of newer CRC32 variants that are better than the CRC32 that everyone uses. In fact, you can see these were discovered by Philip Koopman, who is a professor at Carnegie Mellon, and he's done a bunch of research into the best CRCs and maintains a webpage here with his findings. So this is what he calls the best CRC polynomials. And he breaks them up into the size of the CRC. So we've been looking at 16-bit CRCs, but we can go down here and look at 32-bit CRCs. He represents them in kind of a different format here. He represents them in hex. But basically what he's saying here is for 16-bit CRCs, what is the best CRC in terms of giving you a certain Hamming distance for a particular size message? So if you remember in my last video, I talked about Hamming distance, and Hamming distance is the minimum number of bits that you'd have to change between two messages in order to not detect an error. So in this case, a Hamming distance of 4 means that you can change any 3 bits in the message and guarantee to detect it. And he says this particular CRC will give you that, and it'll give you that for messages up to 32K long. You can get higher Hamming distances, but you can see the message size gets smaller if you use these other CRCs. But the neat thing is, you go to look at the 32-bit CRCs, some of these are really quite good. I mean, 32K message, you can have a Hamming distance of 6, so guaranteed to catch at least 5 or any 5 errors in a 32,000 byte message. That's not bad for only having to add 32 bits, just 4 bytes to your message. 0.01% overhead to protect a message like that. It's not too bad. But random one-off single-bit errors are not the only type of error that you might want to detect. One of the most common errors in data transmission is burst errors. And one of the most important properties of CRC is that they're really good at detecting burst errors. So what is a burst error? Well, it's a bunch of potentially errored bits here in a row like this. And technically, the way we define it is it's an errored bit followed by some number of bits that may or may not be errored, followed by another errored bit. And then the distance between the first errored bit and that last errored bit is the length of the burst. And it's important that the ones in the middle may or may not be errored. So for example, if you just had all ones in here, that would still be a burst error, right? Because the first bit is a 1 when it shouldn't be. The last bit is a 1 when it shouldn't be. And the middle bits, some of them should be 1s, some of them shouldn't. But if they were all 1s, then that would be a burst error. And that's, an error that could happen in transmission. You could have just some glitch that causes nothing but 1s to be received. Same thing with all 0s. That could be a burst error as well. So mathematically, the way we look at this is with this expression here, which is this thing with 2 factors. The first is this x to the I that shows how far from the right the burst error occurs, x to the I, and then k is the length of the burst. So like we saw before, if our generator has more than one term, then this x to the I is not going to be a factor. So we don't need to worry about that. We just need to worry about this factor here, this polynomial, this k degree or k minus 1 degree polynomial. Well, as long as this k minus 1 degree polynomial, the degree of that polynomial is less than the degree of our generator polynomial, then the remainder can never be 0. So let's say k is 16. This is a 16-bit burst, which is what it is. K minus 1 would be 15. So this term here, or this factor here, I guess, this polynomial here, this k minus 1, is going to be a 15th degree polynomial. Well, if our generator is a 16th degree polynomial, that's not going to divide into that. And so it doesn't even matter what our generator, as long as it's a 16th degree polynomial, it's not going to divide into that. And then it's not going to divide into this factor here if it's got more than one term, as we saw before. So this polynomial, in fact, pretty much any CRC polynomial is going to have this property where it's guaranteed to detect burst errors that are smaller than or equal to the size of that polynomial or the degree of that polynomial. So in practice, any 16-bit CRC is always going to detect against 16-bit burst errors. A 32-bit CRC is always going to protect against at least 32-bit burst errors and so forth. So now if you take a step back and look at all of this together, I hope what you're starting to see is that CRC gives us this really powerful tool for detecting errors and being able to analyze the types of errors that we're able to detect. So we have this tool to be able to model the types of errors we're detecting and even generalize that. And then we have these mathematical tools to be able to evaluate whether a particular generator polynomial or in other words, a particular implementation of CRC will detect that type of error or how well it will detect that type of error. And it also happens to be the case that the types of errors that we would detect in a communication network or something like that are also the types of errors that CRC is able to detect quite well. So this is all well and good and everything, but this seems like quite complex, and tedious too, to have to do all of this computation and everything to figure out what that CRC is or to evaluate whether a CRC was received correctly. If we go back to where this video series started, we're trying to send data from one computer system to another and evaluate whether we receive that correctly. And so when we looked at parity, that was actually quite simple to implement in hardware like this. But if we look at CRC, this is way more complex. How are we going to go about implementing something like this in hardware or even, in software? It seems like it might be a bit of work to get this working. Well, it turns out, and this is one of the coolest things, is that in addition to all the mathematical rigor that you get with CRC, it turns out to be quite straightforward to implement in hardware and to do all of this, tedious math that we've seen, to do that in hardware quite straightforwardly. And so in the next video, I'm going to show how we can do all of this math that we just looked at in hardware and come up with the same answer. Because it turns out that with just a couple chips, we're able to do all of this math. And as you can see, the answer we come up with here is the same answer that we got when we did all of this complicated division. And this is in fact the CRC that we computed for the same message here. And so in the next video, I'll go through how to build this hardware and more importantly, why it works.